Это типа летит протонные пучки, да? Вот они летят, летят, летят. Да, я слышал. Соня, подожди. Соня, постой здесь. Соня. А, вот, видишь, вот структура.
Today you are going to visit the CMS Detector. Just to have a brief introduction, what are you going to see and what we are doing here is that in experimental particle physics, we are trying to answer to some of the basic questions of the physics. For example, what's the origin of the mass, and what are the fundamental particles in the world and the rest of the particles are made of from them, and how these fundamental particles interact with each other. So we're trying to answer to these questions. It may not be useful for anybody at all. But at least these questions are the open questions in physics. Maybe at the moment these questions and answers are not practical or not for today life, but maybe in future these will help us for technology and so on. So in here at CERN, which is a center for studying the nuclear physics but not related to nuclear energy and nuclear bomb at all, be sure about this. Actually, we're dealing with high energy physics, which the energy are even more than the energy of the nuclear physics. But the point is that we do not store the energy, right, to be able to use it for electricity or for not useful uses. We do not store the energy. Here we have under the ground, we have a huge tunnel. This tunnel is about 27 kilometers in the border of the Switzerland and France, something like 100 meters under the ground. And in this tunnel we have a pipe, a huge pipe with two specific beam pipe inside the large pipe. So the aim is to accelerate the protons. To get the protons, we have the tank of the hydrogen atoms. You know hydrogen. Hydrogen with oxygen actually makes the water that we drink. So we have the hydrogen atoms, which is a gas. We inject this hydrogen to some pipe and we get the electron from the hydrogen. You know, hydrogen atoms has one electron and one proton. Electron is a negative charge, proton is positive charge. So we get the electron, what remains is just a positive charge protons. And then with some electric field and also magnetic field, we require the bunch of the protons, which contain about 100 billion of protons together. We require them to circulate in the circular path. At the first in a small path, maybe of the diameter of 100 meters, and after that in the super proton synchrotron, which is something like 1-2 kilometers. And after that, in the circular path, we will have two bunches of protons. We inject them to the Large Hadron Collider. One of them will circulate clockwise, the other will circulate anti-clockwise, right in the beam pipe of the tunnel. So we actually fill these bunches, so these bunches will circulate, then it may take 8 hours for them just to circulate, right? And during these 8 hours, at some special masses, for example, at some special points, like here, 0.5, we bend the path of these two beams, and these two beams actually collide. So we let these beams to collide, and then there is a collision, there is a huge amount of energy that is produced, and this huge amount of energy can be changed to the mass and vice versa. From the Einstein equation, we know that energy is equal to the mass. It means that they can be transformed to each other. So if you can produce a huge amount of energy, this can be transferred to the massive particle. And also massive particles can decay, they produce huge energy, and also they can decay to the lighter particles. so far, from the hydrogen atom, we take the electron and we require the protons to circulate in a beam. Well, the idea is just to smash these protons together. But we know that if these protons are very, very high energetic, then the collision will produce huge amount of energy. It is just that if in a street, two cars just hit each other with a very low speed, what happens? Nothing, just some scratch in front of the cars. But in assume two TGV, high-speed train, and in unfortunate case, suddenly in one rail, they hit each other. What happens? The explosion will happen. So here, the idea is to get protons very, very high speed. So at the time of the collision, a huge amount of energy will be produced. When we accelerate the protons, their speed approach to the speed of the light. Yeah, the speed of light is 3 times 10 to 8 meters per second. Well, I mean, this number, we cannot imagine what's that, but just tell you that a photon, which is a light from the light which you see, in 1 second can circulate 7 times around the Earth. Just in 1 second, a proton can circulate 7 times around the Earth. So, when we accelerate the protons, their speed approaches to the speed of the light. And at that case, we smash and collide the protons in this beam to the protons from the other beams, and you can imagine that a huge amount of energy will be produced, and by this energy can be transferred to huge and massive particles which do not exist in their usual and natural way. They just can be made artificially, and because they're not stable, they decay very quickly to the different lighter particles.
But this energy when it collides, there's no sound, there's no, it's not, you can't see it.
Yeah, we cannot see it. There
No
is not
sound.
specific. There is no such a specific sound. Yeah. Electricity that this machine and also detector consume is the same as the electricity that the Geneva city consumes. So you can imagine that it's too much, actually. So far, we accelerate particles and collide, but it's not enough. We don't know what happened by this collision, right? It's just some particles collide with each other. So what? After that, what happens? As we collide the particles, we create a condition or situation which looks like the condition at the early stage of the universe, 13 billion years ago, which we call it Big Bang. You know, we believe that our universe starts from a point, from an explosion, which we call it Big Bang, and after that, all the universe, which was just a point, expanded, and even now it's expanding, and our universe gets larger and larger. So we believe that this explosion happened 13 billion years ago. At that time, there had been lots of energy at the same point, and lots of energy means high temperature, billion degree of centigrade temperature, right? Energy and temperature also have a relation to each other. So by colliding the particle, actually we create a huge amount of energy, which means also a huge temperature. So at just a fraction of a second, we recreate again another Big Bang. Yeah? When you create a condition like a Big Bang, it means that you recreate the Big Bang again here. But not what Big Bang, lots of Big Bangs in a second. So
It's very hot then.
yes, very, very hot. At that center, very hot. But this hotness will not endure for a long time. It's just for a fraction of time. Why? Because also, if you produce this together, a massive particle will be produced. This massive particle, which is very hot, will not stay for a long time. This will decay just in a 1 billionth of seconds, or even less. So far, we accelerate, collide. But now we need a huge camera to take a photo of what had happened. Because, you know, we cannot see anything. Yeah, we need a very sensitive camera to take photo, and we need to record all this information somewhere. Then we go and look one by one what had happened. So at each interaction points, we need a huge camera or detector, right? But there is a difference between the huge camera that we're now going to see inside 100 meters below the ground with the usual camera. Okay, let's enumerate the differences. You tell me, what are the differences between this camera and the detector downstairs?
That's high speed.
Yeah, true. The speed of that is high. One of them is the size, right? The camera that you have weights, for example, 200, 300 grams, half a kilo or 1 kilo most. But the camera downstairs is 12 million kilograms or 12,000 tons. So it's very heavy, right? 12 million kilograms or 12,000 tons is very heavy.
But does it record actually?
Yeah, that's a record. That's one of the heaviest detector in the world.
Atlas heavier.
What?
Atlas heavier, yes.
Atlas is heavier, right? It's a bigger. But CMS has something different with respect to Atlas. Okay, the other difference is the size, not only weights. Yeah, these are just 10 centimeters, 20 centimeters, but our detector, our camera is actually 25 meters length, 10, 15 meters height. So, it's bigger. The third difference is that when you want to use your camera, there is a scene, there is a beautiful lady or a handsome guy over there. You want to take a photo of him or her. Okay, so the event is outside of your camera, somewhere else, right? But our camera is such that the event will happen at the center of the camera. Our camera is a cylinder, right? It's a cylinder. Also, it's like onion. There are several layers. So you cannot imagine a cylindrical onion. Yeah? It has a barrel, central barrel. Also, it has the end cap. And the beam pipe is actually go in the middle of this cylinder. So the collision will happen at the center of this camera, while the event is over there and just take the photo. So actually this is, I would say, a two-dimensional camera, yeah, which the photo will be just in a two-dimensional plate, while in our case we have a three-dimensional camera. It's a cylinder, and also at the center that event happens and different particles produce and they go in different direction. But the most important difference with respect of these cameras with respect to ours is that by usual camera, a question, how many photos can you take in 1 second? How many? Seven, 10. At most 10, very good, yeah. But with our camera downstairs, we can take 30 million events per second. 30 million photo or event per second.
When does it know when to take the pictures? Does it always take pictures?
Yeah, always take pictures. Yeah, for example, in a day, in a field.
It's a lot of pictures.
Yeah, exactly. Yeah, 30, 40 million pictures per second. You can imagine per hour how much per day, per year. Actually, the machine does not perform or run 24 out of 24/7 out of 7. But I would say maybe 1/3 of the year it works and it takes photos or it records the
You look
event.
at all of them to see when you got it right, or
Yeah, I'll explain that. Do we really keep all of them or not? I'll talk about this later.
How much computer data they produce per second?
Well, the size of each event is something like 1 megabyte. So, in 1 second, 30 million megabytes in 1 year.
Yeah.
But we will have a triggering system which actually do not record all of these events. Well, for example, you want to take a photo of Eiffel Tower, right? You take, for example, 10 photos, but some of them are blurred and some of them your hand has been shaken, so you don't, actually you delete them, just keep the perfect one. I'll explain later what does the good events mean that we really would like to save, and actually we throw lots of that away because we cannot keep them and they are not interesting. So far, you've got an idea that how fantastic this camera and detector is. Several properties, very large, very sensitive in terms of the timing and so on. So this detector, let's from now on call it detector, not the camera, yeah, but it's like a camera. this detector is a three-dimensional detector. It has a central barrier part with different layers and also different end cap. The aim is actually to cover totally it. So when the beam of particles, protons, they collide with each other, different particles at this center will be produced. We have initial particles which are protons. We have a final particles which can be anything. Electron, photons. Yeah, please come here. So please go over there. Okay, what was talking about?
About the particles.
Yeah.
Producing particles. Yeah.
I was talking about the feature and the shape of this detector. It's a cylinder. There is a barrel with different layers and also end cap, and the aim is to cover all the particles that go in all directions. It consists of different sublayers, right? We need to have different sublayers because different particles are produced. How? Suppose that you have a light. Yeah, from flash you have a light. If you put a piece of paper in front of the light, what happens? This piece of paper will stop the light. Light will not go at the back. There is a shadow of this here, so it will be darkness. So this sheet of paper can stop the light. But instead of light, if you have a dart, if you want to throw a dart, the dart will pass through the paper, right? It's not enough for a paper to stop the dart. For example, you need a wooden stuff, a wooden sheet. Dart will go to the wooden sheet and then stop there, right? So we need a wood to stop the dart. But a bullet, suppose a bullet from gunshot, it passed through the wood also. But then you need to have a special gilet, which policemen they wear, right? In order to stop the bullet inside there. It's a very heavy from a special material. So that special gilet needs to stop the bullet. This is exactly similar here. When we collide particles together, different type of particles like light, dark, bullet, I mean all kinds of particles will be produced. Yeah. So in order to identify them, to see what are the final states, just to reconstruct the event, to know that this event has this particle, this particle, this particle, and this particle, right? We need different layers from different materials. Each kind of particles will interact with just a specific part of the detector. For example, electron pass through the detector and deposit the energy in the electromagnetic calorimeter. Ion will go and deposit energy in the hadron calorimeter. Mu1 will pass through this layer, this layer, this layer, and they interact with the, for example, the last layer, right? So by looking, we cannot see these particles at all. These particles are very small and they move very fast. We cannot see them, but we can see them that they have already affected, influenced some part of the detector. For example, when an electron passes through the crystal electromagnetic calorimeter or pass through the tracker, there are several layers of tracker. Then each of them will create a hit. One hit here, the other here, the other here. Then we connect this hit together and we found that, okay, we already had a particle which passed through these hits, and this is the path of this particle. So this is the reason that actually we make these huge camera or detector from different type of the material. I'll explain downstairs to you that what are these materials. There are sometimes strange elements from the Mendeleev table, which maybe you've never heard about these elements. I'll explain you downstairs.
With the guide.
Yeah, please come here.
Please go with the guide, the one I'm find. Les Français ici. Les Français.
Et nous, on va les laisser prendre un petit
Yeah, actually I'm not very expert in stuff detectors, but I try to Here is the cross-section section of the end cap of that cylindrical detector. This is just a part of the end cap. You can take as much as photo as you like, then I'll explain the rest. The boarding parts, I'll explain the boarding parts to you. You can take photo of interesting parts. Yeah, that's the, from here to there is actually, like 15 meters. Not this part, the whole part. Yeah. No, yeah, this is just one slice of the detector. You look at there, we will go until there and see all the two parts. So, during the collision, all these parts will pack together, right? This is just for illustration and for public show. During the collision performance of the machine, all these parts are together, this part, the rest next of us. And you know, all of these parts are movable by these hydraulic jacks. So, can you imagine what's that? That's the beam pipe. Yeah, that's the beam pipe. So, that will be connected to the LHC, Large Hadron Collider, to 27 kilometers, right? That's coming from there and needs to go from the center of this and then go from that way to that. So actually that's part of the 27 pipe. And that green pipe, it needs to squeeze the particles because you know protons are very, very small in terms of the size. So in each of the bunch of the protons, which is just 10 micrometer, there are something like 100 billion protons. They are so very, very close together. We need exactly to check if when we want to collide the particles, they are just head-to-head, right? We call it head-to-head collision. It means that you increase the probability of one proton from this bunch to collide with this proton from this bunch. So you need to squeeze them. This part, the red one, is actually called the iron yoke. So I'll again explain to you what does that mean. We have different parts from tracker, from calorimeters. After tracker and calorimeters, we have a magnet. You know about magnets. You have experience using magnet, for example, putting beautiful stuffs in your refrigerator door, yeah? That's the simple example of the magnet. But we already have a huge magnet from the Earth, magnetic field of the Earth, right? When you put your compass, you can find the direction of the North Star based on the very strong magnets of the Earth. But the magnetic field that we produce with our magnet or solenoid is 100,000 times greater than the magnetic field of the Earth. So you can see that we produce a huge amount of magnetic field. This is the record. We do not have such a stuff in the world. At this size, we're producing this magnetic field. It is called 4 Tesla. This is the size of the magnetic field of the CMS, which is also greater than this Atlas. In Atlas, they have a 2 Tesla magnetic field. Here we have a 4 Tesla magnetic field. So, yeah.
When the machine is, when it's all working, how fast does it turn?
It does not turn, it's fixed. It's just fixed. Everything is fixed during the collision. Just everything is packed together. Now we have put them away just for you to have a view of the section. Everything will be packed together.
How?
These are movable. You see these jacks. You can move these stuff. You can also move that stuff. Actually, there are several stuff over there, right? So we can move everything together. So this actually will cover, if something happens at the center of this cylinder, particles will go in all directions, and actually all of them are covered from here, 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 here. So we do not want to lose any track, any particle.
Was this made in Pakistan?
I don't know. Kawasaki might be for the company in Japan. But I know that these parts, some part of it are also made in Pakistan and also India together.
What is made in Pakistan?
The muon chamber. This is what also muon chamber is based on that. I'll also show you the specific part of the muon chamber. More than 40 countries involved in this project. Pakistan was that, India was that, also Asian countries, also Iran, which I'm coming from, and Europe, United States, lots of countries actually work in that.
And what?
This is part of the beam pipe which is going to squeeze the beams. Yeah.
If you're understanding well, this is close otherwise. That means here, this is a moving part.
Yeah, exactly.
How long does it take to move this all? How long?
Yeah, it's very slow, but not as slow as the time that we bring everything from top to here. I'll explain about that script to you. Okay. This is part which we call it the hadron calorimeter. This is the end cap of the hadrons, right? And inside it is electromagnetic calorimeter. These are the red one is iron yoke, which aims to keep everything together, and between the iron yoke we will have the muon chambers. So the muon chambers are actually some tubes which are filled with a special element called niobium titanium. That's element, niobium and titanium. So these gases are filled in this area. When a muon, actually you can see it's made from INFN in Italy. Yeah, it's just over there.
So now all this gets together.
Yeah, everything gets now it's you see it's just show this, but everything will go together. It will be quite packed system. So when a muon from the interaction point, they pass through these different layers. For example, they pass through the gases, right? They interact with these gases and they release electron. Then electron will move from the negative pole to positive pole. When the electron passes, actually it produces a small voltage, and this voltage will be transmitted via some wire to the computer and read out the electronic system. And from that, we will be notified that actually a muon has passed. And we have different layers, so this will help us that after this, muon will go to this direction, then goes to this direction, then goes to this direction. We will have a path of the muon. We can measure the bending, the curvature, everything, and we get the information of the different parts. So the question that I asked previously was that, why do we dig something like 100 meters? One of the questions might be radiation. Yeah, somebody mentioned to the radiation, but it's not the only reason, because we could just make this 10 meters and it's not 100 meters down the surface, and it would be safe in terms of the radiation. Yeah, we could do it, we could protect it by 10 meters down. But the main reason is that these stuffs are very heavy. Near the Geneva and also the Jura mountain, all over this area is soil. We cannot put 12 million kilograms on the soil, so we have to dig to reach the rock. Yeah, in this area, we had to reach to the rock, and the rock at this area is just accessible in 100 meters under the ground. So this is the main reason that we dig to go like this. So all these massive detector is based on the rock, and it's not visible for you, but if you put a ball here, you see that there is also steep, there is a slope of here. This slope is the slope of rock from the Jura mountain to the Geneva lake, but it's 1.5 degrees. You cannot find it like this. This is not something like this, but very, very steep slope. So if you put a ball here, this will actually move in this direction. So exactly you have to follow the rock at the ground, yeah. So that's the modern calorimeter, right? This part, this also is what that is. And the beautiful magnet, the impressive magnet that I talked about is this one, right? This is the silver one is actually the magnet crown here. And that hole is the interaction point. Do you see two stands, two places for beams, right? These are actually two different beams.
What's the silver?
This silver is magnet, solenoid. Yeah, you can see. Not this one, but that.
Oh, there.
Yeah, there. Some sheets of magnet. So if you look at this, you see two passes of the pipe, right? These are just for the clockwise and anti-clockwise protons. We just at the center we bend them. Yeah, please come here. We bend them, and after that we have a tracker, calorimeter. These are our calorimeter. We have this one made from the brass. This part, I think electromagnetic is like that.
Сейчас увидим. Давай.
Nearby. Them are performing well during the experiments. Good question. Well, all of these are actually connected to the readout electronic system, and we will monitor them very simply. For example, for a cylinder or for a disc of the for example, the sub-detector, we will have the slice in our computer which normally should show everything in green. Small pixel green, different discs, right? We look at these histograms and this distribution. If some part is not working, then it would be red. Then by looking at this one, which are online, when it's working, we will refresh the status of these discs and these layers at all times. We see if some parts are not clean, then there is a problem here. Probably we need to solve it, maybe not at that time, but at the first technical step.
Где?
Yeah, if it is open, then we will see what's going on in 100 meters above us. So all these different parts of the sub-detector were made in different countries all over the world. As I mentioned, 3,000-4,000 scientists, physicists, engineers, technicians are working in CMS from 180 institutes and universities all over the world from more than 40 countries. So it's a really international collaboration from every country, not every country, but lots of countries. So these different parts are built and then carried out to Geneva, to here, at the assembly hall. There is a large assembly hall just on top of this shaft. And after that, with some hydraulic jack and crane, they are lowered. These parts are lowered from the shaft to here. As these parts are very, very heavy, we cannot lower them very quickly because at some point they may get out of our control and they may suddenly fall, and actually you miss the billion Swiss francs which you already have paid for this. So you have to do it very, very gently and slowly. So each part for the movement, for lowering, had taken 10 hours just to be lowered from the top to here, which is 100 meters down. So 10 meters per hour. So for each of the parts. Then this part has been lowered from top to here. Then they have been pushed, some of them has been pushed to that place, the other has been pushed to that place. When the lowering is completed, then we have put together everything together. We have a white pack detector, and then we restart the detector to get data.
How many years have they been working to construct this?
Yeah, upstairs. Okay, the design was something like 1997, 98. At what time it was designed and also approved. The procedure of building starts something like 2000, and it was completed in 2008. So I would call it in total something like 10 years. So it stopped working in the end of 2012. In 2013 and 2014, there will be more data. We will upgrade and get prepared to go to the higher energy, and we will hopefully restart by the beginning of 2015. Yeah, if you want, you can take a beautiful photo here. Okay, concerning the magnet or the solenoid that I talked about, this solenoid works at the temperature of minus 207 degrees, right? And actually, as a magnet, it can store a huge amount of energy inside. So, in terms of the quench, when there is a sudden shutdown, right? Then what should we do with this huge amount of energy which will be stored in these magnets, right? The magnet energy is stored. The energy is so huge. So, in case of the quench, which we call it the sudden shutdown, we should take care of this energy which are here. There are some special cable and wire connected from the magnet to the top, yeah, which at that case can quickly transfer the energy of the magnet to the top. Just there won't be any explosion here. The energy that are stored in the magnet is equal to the energy of the 500 TNT at the explosion. Can you imagine 500 TNT, the energy of the magnets? Let's go. Yeah, okay. So that wire actually makes it safe to be sure that even if unexpected event happens, we will be safe in that case. Okay, let me explain about this gate. This is the gate actually for the people who want to come from this side. This is the gate, the last gate they want to enter. So during the experiments, when there is a, for example, shut down for a few hours or for a few days, the expert, the technician, need to pass through this gate. So when they come here, they have an access card. They show the access card here, then their name will be written here. then the shift leader at the control room will be notified. You should wait in front of that camera. The shift leader will look you, and if he confirms that you are really the one that also having this guy, then he will push the button. You will get the key from here. You can, by this key, open the door. If you open it, that door will be closed, that door will be open. You go there. There is eye scanner. You have to look at this eye scanner. These already have the information of your biometric information there. And then if you are recognized, then this door will be closed, the other door will be open, and then you are allowed to enter, unless in that case. And unless you get back the key and put it over there, the whole system, the whole motion detector in these 27 kilometers will not stop. So we will be sure that nobody will just trap downstairs and the machine is working. Just to not miss poor physicists and technicians. Okay, so here is the view of the tunnel. The door to the tunnel is from here. We're not allowed to enter, but I mean, what you have seen in Curiosity is the most interesting things which you could have in NX experiment rather than also as detector. These are the beam. Actually, they are circulated 27 kilometers. There are several dipole and quadrupole, which actually lead the beam to be in exactly circular path, right? It should be exactly in a circular path. So the protons are charged particles. When they collide in a circular path, they get energetic. The more they rotate, they get more energetic and they get more speed. So they can reach the speed of approximately the speed of the light. Okay, we go. So, who can guess what is this sign?
Someone is working, I think.
Do not sleep during the work.
Okay.
Yeah? Apart from the job, what does this sign mean rather than do not sleep during the work? Well, as I told you, we have some gases at the muon chamber. So, there is a probability, however, hopefully very small, that we will have the leakage of these gases. When these gases will leakage, they combine with the oxygen at the air. So in that case, you might have the enter to the case with the lack of the oxygen. So we have some sensors over there which are sensitive to the amount of oxygen in the air. We approximately know that the amount of oxygen in the air is something like 18–19%, right? So if this greater amount changes, then these will be sensitive to that, then they will alarm and activate the alarming system. So you will know about that and then you should run away, but not take the stairs, but elevators. These are actually some readout system, which all the cables that we, or most of the cables that we downstairs are connected to here. And by these we control the different subtemperature and also we control the carrying on or turning of the from over there up. And those are the stairs. Yeah, something like 100 meters should be something like 100.
How many floors of stairs?
We just have 3 floors, -1, -2, -3. So we end up with -3, and by stairs we come to -2. So we get the limit over, which is from -2. There's also -1 upstairs. In between, there are nothing.
Where do you get your electric power from?
We get from the France electricity from ODF. Yeah, we consume, and the amount of electricity that we use is equal to the amount of electricity that is used by the Geneva during a year.
Yeah, they said that you throw away lots of electricity.
Yeah, we also.
Why do you throw away? You can give it to France or to the...
Well, you know, saving them and, you know, directing them, getting back to the system is not... No, Geneva, I think it has its own
Why do you
electricity.
throw all that electricity away? You can give it to France and Switzerland.
Well, you know, I'm really not sure what you mean by throw, but here we waste also some electricity.
But then you waste a lot because lots go into the water or something like that, and you waste a lot of electricity.
Yeah.
Somebody said
This I don't know what they mean by losing them in the water.
Where are they just to go after the...
Donc le caramètre abonné, c'est un peu plus
Yeah,
difficile.
actually,
La lumière scintillante.